All right, how we doing, y'all? Welcome to our E360 discussion. I decided that I wanted to record this beforehand rather than us meeting on a Wednesday night. I thought about it, and yeah, a few of you were like, "Yeah, let's all meet on a Wednesday night, 6:30 p.m. That'd be great." But I thought about it and was like, "Well, I'll just make a video." So let's see. Anyways, let's see if these transitions work. Oh, they do. Oh, okay, and then let me show you this. Yeah, that works too. Anyways, yes, this is my home studio. This is where I do all my other content creation. So anyways, let's get back. So if you guys remember from your guys' lectures, Dr. Siebers introduced you to these Z-transforms. And if you remember, let's see, the definition, if we were to do the following, Z of some signal x of n, all right? And by x of n, I mean like some type of signal like this is equal to, let's just draw something like this. Dot. This is n, that's our x signal x of n. Let's see, how do I want to do this? A of n, and then let's just put u of n. There we go. Does that look good? Does that look like a nice little signal? So anyways, this is the way we're going to define it. So the Z transform our signal, and he's probably said this a million times, we're going to define it as this, okay? X is Z, okay? Memorize it, love it. And that can be equal to, let's look at their whole signal, okay? We're going to go look at the entire signal sum from n is equal to infinity, right? To n is equal to minus infinity of the signal itself, okay? Think about the signal. Multiplied by this little guy right here, z to the minus n, all right? It's kind of similar to what we've talked about with the Laplace domain, if you think about it. Laplace. There we go. Where we did something similar, x of s, right? Which is equal to the entire signal, right? From, what do you call it? The entire signal, right, to infinity of x of t, right? The entire signal, just e to the minus st dt. Remember that? Does it look familiar? Same thing. So we're taking the entire signal, we're adding the entire signal, right? Looking at the entire signal, multiplying just by the z to the n, okay? And that right there, your definition. Learn it. It's probably going to be on your exam. Let's just say if you wanted to throw you an exam question given some signal a of n, u of n, and b of n, u of n, or u of n, let's see, or I don't know, prove something where these are like, I don't know, inbound or in phase or whatever. So I'm just creating some problem. I don't know. Maybe he might do this funny thing where instead of he'll just make you subtract this and just do u of n minus 1. Now you got a pulse. If you guys know what that means, okay? So I don't know what he's gonna throw at you, but those are just examples. So I had someone bark at me earlier saying, David, I don't know. I feel like it's like memorizing, but I want to understand what's going on. So page 2. Anyways, let's see. So I want to show you guys something. It's called the geometric series. Okay. So for mathematics, if you remembered this, let's just say I have some finite signal. Let's go to n, right? And we start at n is equal to 0, right? Let's see. How do I want to do it? A of n, okay? Just some little signal, right? Now let's do the following. Let's just start at 0, okay? A 0, perfect, done, right? Plus A1, okay? Plus A2, plus dot dot dot, plus let's do A of n, okay? Is that good? So let's just define this as This is our summation, okay? This is what we want. We want this puppy. So if I were to define this puppy as S of n, okay, that's what we're trying to do, all right? So the mathematician said, if you do the following, where you grab your magic, what do you call it? Just grab the variable that you're playing with, right? A, we're playing with A, okay? And then I'm gonna write this with a pink marker. What's another marker y'all like? You guys like these markers? S of n, okay? We multiply this series, okay, with the actual play variable, this guy right here, okay? So if I were to do the following, let's start with the first point, okay? A of 0, right? So, but instead, we're gonna have A of 1, okay? Plus A of 2, all right? Plus dot 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 A to the, let's say, n, okay? Plus A of n plus 1, okay? Now someone's barking saying, where'd that n plus 1 come from, okay? Let's think about the series. If we were to rewrite this as A, you got this n is equal to 0 of A of n, right? It's like we're shoving this guy, let's use our nice little yellow marker. We're just shoving this guy into this. Can you guys see that color? It looks green. This is yellow. Anyways, it's gonna look like, what do you call it? Let's see, n 0 a n plus 1, okay? Is that good with everyone? Right? No tricks, no treats, or all treats, no tricks, whatever you want. So now let's get to the final part. All right, so the mathematicians are like, all right, psych y'all, we're gonna put a minus there, okay? Now we're gonna negate all these dudes, okay? So we're gonna put a minus sign right there, so we get the following condition: S of n minus a S of n, all right? Which can be rewritten as S of n 1 minus a, all right? Got it? Because we want this. If I were to do this, we want smiley face. Okay, that's what we want. So now let's start doing the mathematics and just get rid of all these things we don't like. So I see this guy right here, okay, and I see this guy right there, and then I see this guy here and this guy, and then you start drawing this pattern, right? You realize, oh shoes, you're just left with this guy right here. I'll draw the box, and this guy right here, okay? Everything in the middle just cancels out, and we're left with these two terms, all right? So now that turns into the following: a0, which can be rewritten as 1, minus a n plus 1, okay? So now you get to the point where you have, let's just rewrite it, minus 1 minus a of n plus 1. You see this guy right here? We're going to divide this term by this, all right? Which gives us S of n, which is our series. Let's rewrite the definition. N is equal to 0 of a of n, correct? Is equal to 1 minus a n plus 1. 1 minus a, and that is what you're trying to memorize, okay? This is where he gets that proof, all right? So now here's the other part, and someone's like, well, Dave, I don't want to learn this, he shows you this one. I'll show you in the next page. So let's try this. Page 3. Boom. So he went right into the infinite geometric series. He just said, all right, screw y'all, just go to infinity, all right? So I'll show you what's going on. So let me rewrite this. 1 minus a n plus 1. 1 minus a, okay? So first things first. If you have, let's just say our limit, right? Lim as n goes to infinity, right? All right. So what happens when we have a to the infinity, right? Well, what happens? I don't know. First, if a is greater than 1, correct? So it's like 1 point, or let's just think, I don't know, 10. 10 to the infinity. That's going to give you, well, big infinity or something like that. So that limit of whatever's in there, dot, 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 goes to infinity, okay? Understood? So now, and then there's a case where if it's equal to 1, let me remember. Well, if that's equal to 1, then it's just, I guess it's equal to 1. I think that's how he explained it. I'll just put a squiggly line. But if it's is less than 1, all right? So we have like 0.5. So you got 0.5 times itself, which 0.25, and it gets smaller. It gets smaller, very small, right? It converges, okay? That's good. So if you realize it, if we go to an infinity, like, I don't know, 0.99 to the infinity, infinite power, right? You'll start realizing that this term starts going to 0. So we can rewrite this as 1 over 1 minus a. And that's when, what do you call it? You have this following condition. Infinity n is equal to 0 of a of n. Boom. Here's my arrow. Is that good, everybody? Is everyone following? No, nothing's too scary. Nothing's too spooky at the moment. Anyways, now everyone's like, how does this relate to my homework? Alright, so you have the following. Engineer. 0 of, let's just say our signal x of n is equal to a of n, okay? U of n, because I like it, okay? So, well, let's do this. N is equal to positive infinity, right? So you already know, okay? A of n, u of n, okay? And then times that z to the minus n, okay? And this here is the x, z, okay? All right, is that good? So, wait, and there we go, okay? So with this unit step just makes everything easy, okay? So this correlate will affects this little guy to get you the following. I'm making bad infinities. There you go. N is equal to 0 of a of, no skipping steps. No skipping steps, David. All right. Anyways, so we have a to the n, z to the minus n. So we can rewrite this as, is anyone bother if I do this? N is equal to 0, a z to the minus 1 of n. Right? We're good, right? So, engineer, if we just say, I don't know, I'm just going to call, I don't know, fish, whatever, is equal to, no, that's a bad fish, I don't know, triangle is equal to a to the z minus 1, all right? So if you're thinking about this in terms of variables, okay, don't think deep, all right? We can make this look kind of like this right here. Just imagine that a is a triangle, okay? Okay, we're gonna put this triangle, but where's our infinite? Oh, there it is, okay? So whatever's in this box in here, triangles, fish, I don't know, whatever you want, that it goes right there, okay? So this part, if I were to brute force it, you're gonna get the following 1 minus a to the z to the minus 1. And then if you guys wanted to be complete, you can multiply this top and the bottom by z. You get z minus a, and that is x of z. Whew. That was that tough. So that's part 1 of understanding what's going on right here. A similar approach can be done with, let's see, the non-causal. Some people call it anti-causal. I've learned that. Let's see. Where? Let's see. There you go. Page 4. Where, let's just say Dr. Stewart says, psych, y'all are gonna pay for this, and he just says, I don't know, y of n is equal to minus a of n u of minus n minus 1, okay? So if he does this to you, okay, so you're cooked. I'm just kidding, no. Anyways, y of z, okay, you're gonna memorize this one here. And then minus a of n, u of n minus n minus 1, z to the minus n, okay? Minus infinity to plus infinity, all right? This guy right here affects this portion, okay? To the point where you have the condition of minus 1, minus infinity, minus a of n, z of minus n, okay? And then I think he tells you to do some change of variables. I think he says use some magic variable where I think it was like, I forget the notes. Let's see, what does he say in his happy little notes? Oh, Dr. Stewart, let's see, how do you prove this? You guys reading the book, by the way? Is it a nice book? He told me he'll finish it when I graduate my PhD. Let's see, this is the little guy I was trying to prove. You guys see it? There you go. Let me just turn off my face cam. Oh, it doesn't turn off. Oh, that turns it off. Okay, great. Anyways, he says k is equal to minus n. Okay, so he does the following. Let me show you. Let's split. Okay, you guys like that? So he says, okay, assume k is equal to, what do you call it? Minus n minus 1. And the reason why he wanted you to do that is so that, let's see, why did he want you to do that? Well, you're going to do this. It's going to give you minus k minus 1. So I think in that terms, well, this right here is n is equal to that. N is equal to minus infinity. Let's see. Guess that's how he wants you to do it. Well, let's start brute forcing things, okay? We're here to learn. So this is what he wants. He's like, yay, smiley face. Anyways, I'm going to put minus k minus 1 is equal to, what do you call it? Minus 1, okay? And then we got minus k minus 1 is equal to minus infinity, all right? The point where, how did he want you to do this? Let's see. Well, this is our summation, by the way, okay? Let me think. Why did he make you do this? Crazy substitution. Well, if you think about this and you multiply this whole thing by minus 1, you get the following. K is equal to infinity plus 1. So I guess, well, if you have that top part, if you have this top part right here, right? Well, this cancels out and this cancels out to the point where, let's see, k is equal to 0? Question mark? Let's think about this. But the whole point that he's trying to make you do is so that this top part becomes infinity and this becomes 0. So if I were to think about it, well, he says this. Minus a z to the minus, no. This is plus 1. This is minus 1. There we go. Then you do something with this guy right here, okay? To where you get z minus 1 minus k minus 1. And then if that flipped, that means k minus 1. Oh! Okay, engineers, I figured it out. So, hear me out. K is equal to 0, k is equal to infinity, okay? So you know this is a summation, right? And I don't know why it ticked onto me. So we're used to, when we see something like this, or I don't know, n, and then I is equal to 0, right? We're assuming we're going 1, 2, dot, 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 n, right? This one is assuming we're going infinity, infinity minus 1, dot, 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 1, and then 0. So we're going backwards. Okay, we're going backwards in terms of like solving this equation. Okay, you see, this is why I enjoy doing these kinds of things with you guys. Teaching helps me become teaching to the students also improves the research and teaching of the instructors and graduate students. Anyways, let's rewrite this. Infinity, 0, okay, k is equal to 0, k is equal to infinity of this a to z to the minus 1 minus k to the minus 1, okay? And then, what's his name? You gotta just flip it, okay? Just flip it, all right? K is equal to infinity, because we like the infinity on the top. K is equal to 0, all right? There you go. And then, is anyone bothered if I do the following? Well, here's our a minus 1 z. Is that how we want to try and do it? A minus 1 z, and then we have a z to the minus 1 minus k. Is that good? Anyways, and then, well, we chug in. Okay, so this guy is a constant, not affected by k, okay? So we can pull it out. So pull this puppy out, okay? Boom. So a to the minus 1 z, and then we're gonna do the following: infinity to 0, k, okay, of a to the minus 1 z, okay, and then this becomes a k, positive k. Is that good? Is that what he wants you to do? Are you really sure you want to do this? Well, because then this starts looking like what we did earlier back right here. Okay, we got that positive exponential, whatever is in this box, triangles, fish, I don't know. And then we can rewrite the following: a minus 1 z, and then this becomes, and that's infinity, okay? 1 minus whatever was in there, a minus 1 z. And is that it? Yeah, that's it. That's pretty much it. And then if you realize this, you can multiply, what do you call it? There's a minus sign somewhere. Where do you put the minus sign? Oh, so I'll show you what I messed up too. All right, let's see. Where's page 4? So we had a minus sign in here, and I completely forgot to. Here's our minus sign, okay? That minus sign has always been there, so if I just put a minus sign there, okay? You see that? And then here's my minus sign. Here's my it's always been there, okay? And then if you, what do you call it? How do I want to show you this one? Well, this one you can just rewrite it as if you wanted to. 1 minus 1 of, what do you call it? What do you call it? A, and then z to the minus 1 of 1 minus a to the minus 1 z. Is that right? Is that how I want to flip it? Because I'm trying to bring this one down. Okay, we bring it down, then we multiply. Okay, and then this cancels out that, so then you get the following: minus 1 of 1 minus what do you call it? No. Hold up. A z to the minus 1 and 1. Okay, we get that, and then this minus sign flips it back to, what do you 1 minus a to z minus 1. Okay, and then now you got to think about your condition where you have to assume that what do you call it? Z over a is less than 1, therefore your z has to be less than your a. Okay, and then make sure this one's, the pole is what do you call it, inside there, so it's stable. Okay, so don't forget this condition, and that's your proof of what do you call it, our original signal, which was the z transform of minus a of n, no, minus a to the n u of minus n minus 1. Okay. Oh gosh, that was a big hoopla right there. So anyways, is that making sense from what I'm trying to explain? So if you memorize those two, you're completely fine. So those were the two questions that people were asking me about. And then that was page, what page was that? Page 5. You guys keeping track of how I'm doing this, so I can make sure I can give you guys these notes. Anyways, let's see, what's our next part? Let me see, how did I want to show you guys this? Let's see. So, let's see. I think the other thing I wanted to show you was residues. Do I want to show you residues? Yeah, let's get to your assignment. So I'll tell you this. I have my own personal MATLAB, and I did not buy the control toolbox, so I wasn't able to complete the assignment in terms of my personal account. But for, what do you call it? Continue working. But for your student edition, so you can get MATLAB working. So I don't have it downloaded, but I can just get it popping right there. So let's just see what I wanted to show you. I think, where was it? Was it this guy right here? Homework 6. So if you guys haven't seen it, and I thought about how I wanted you guys to do your assignments. So we went over this the last class. Simple little resonator. It's cosine omega. You got this square term, and it wiggles around. You see this pi over 4. And then let me see if I can pop these puppies out. Let me see. 360. Let me open with Notepad. Double click. Ooh, cool. You guys don't see what I'm seeing here, so let me see. Let's copy this first part. Boom, boom, boom. Let's copy this. Boom. And then put this right here. Copy paste. I already got you a head start. So if I were to run this, there we go. Is that looking good? Hello. There you go. You guys like that? So that's what I was able to show you guys the last class, which was how to do Z polls and look at what they're doing. So here's a food for thought for you guys. So you see these poles right here, and they're pretty pointy. Actually, if you want them to be a little more cleaner, let's see. Let's do 0.25. Run that. Oh yeah, looking clean. So it looks a little more clear. So what's his name? But yeah, you can either for your play field right here, you just need to figure out how to just put everything into the Z. This Z is a matrix. If I were to open it for you, let's see, run it. You see, it's just a square. Like here's -2, here's 2i, and we're just going down the numbers. No one's seeing it. Okay, David, you're going too hard. You're going too fast. Okay, whatever. Like that? Turn that into me, you get a 0. I just get it now. -2, -1, 0, 1, 2, and then going down. -2i, 1i, 0, 1, and then here's your center. That's your. The whole point of that mesh or using for loops is just to make your life easier. Personally, I think this right here is the meta right here. So mesh grid makes your life a lot easier. It's what you want it to do. Set up your play field so that your Z reals do like this, and then your Z imaginaries do that. Then you just add them together like that. So anyways, polyval evaluates everything in that matrix. So if you think about this, so at this point right here of Z, so it looks at Z11, and it just does that calculation. Boom, plug and chug, you're done. And then it does it for every point, and it gives you back that same 5 by 5 square, n by n, or square by square, whatever you want to call it. So this theta right here, I try to draw a circle, okay? The precision, I don't think it mattered, no, but this precision matters for the Fourier transform, which is right here. Let me show you. Someone who doesn't want me to show you. Let me see. Okay, we got this there. So here's our Fourier transform, but let me see. I wonder if that's gonna work. Because usually, okay, this is our circle, okay. That's our circle, okay. Yeah, let's try it. Let's try it. I want to see what's going on. Let's see. Boom. Run that puppy. Okay. Let's go back to. Where's my precision? Right here, DZ 0.001, because we're using MATLAB's resources. Woo, let's go, baby. We froze. Anyways. Oh, I don't think MATLAB Online liked that we are wasting water. Because this is all on MATLAB server, so we can crash it or whatever. 0.001. I don't think that's what we want to try and do. I don't think so. Don't do it. Let's see if it works. I don't know. Nope. Oh. Did it crash? Okay. Just delete it. Anyways, don't do that. DZ 0.5. Just that's enough. Okay. Boom. Easy. Okay, and then the Fourier transform. You see these peaks right here? This is your filter, okay? So if I were to, someone doesn't believe me in the filter. If I were to just chop this circle in half, okay? Actually, you can do that right here, pi. What does this look like? Bodhi plot. Hey, where's my Bodhi plot? There we go, Bodhi plot, okay? So if you think about it, this is our highest frequency that we're sampling, and then this is our Nyquist frequency. You're going to learn about that in 480, EE480 with Dr. Siebert, or whoever you want to take it. That's considered whatever signal goes past there, there's no return. It just aliases. You won't see it. Things here look like DC, and things here are, so your fastest signals were actually right here. Yeah, it's right here. If I were there. But yeah, that's your ringing, okay? So if I had some funny signal here, it's going to be the funny signal, plus there's going to be some ringing in that system. So if I throw in a sine wave, you'll probably see that. Anyways, how do I get rid of this ringing? Well, let's look at our poles, okay? So this is where I want you guys to start thinking intuitively, okay? So you see that pole right there? Let's push it this way. Let's push it closer to the origin. So if I were to do the following, I don't know, 0.5, whatever. Oh, look at that. It looks smoother. Okay, looking good. Let's do 0.1. And now it looks something like some bezel filter, or what do you call it? Really nice. So let me show you what a bezel filter. You see, it looks nice. Something like this. Yeah, look at that. some really nice curves, and then butterworts. I don't know. You'll learn that in our higher level filters classes. Anyways, you see, it looks cool. Okay, but anyways, then what happens if you do, I don't know, 0, 1? Then, well, actually, let's look at the C diagram. Well, that don't look good. The 0 and the pole cancel out, so it just looks like, well, nothing. It just, yeah, it doesn't. We'll analyze it. We'll take a look. Let's just do 0.8 for now. Okay, it looks pretty nice, pretty cool. We got about 9 dB at that ringing frequency, but your job is to tell me, okay, 9, if I were to do that. All right, tell me, engineer, what is that peak? 0.25, right? 0.25 more normalized frequency, a quarter of our frequency. Let's just do this as 8. An eighth, what is that? 1.125. Is that making sense? Okay, and then let me do, I don't know, eighth, or I don't know, half. Let's try half. I don't think that's gonna work. Half. You see the frequencies? Are you understanding what's going on? Is that making sense? Okay. Anyways, let's return that back to fourth. Okay, I chose pi over 4. I think that tutor made you do pi over 7, which you could understand it, but honestly, I'd rather you guys think, or not think, just look at the number and no thinking, just understand. Anyways, let's see. So the Fourier transform, I wanted to map this on a real line. So if I were to do the following, omega is equal to the theta. Okay, same thing. Well, I just lose precision there. So let's just do 0 to 1. Yay, it's curvy. Then yeah, it doesn't like scalar multiplication. I know. There we go. Anyways, let's continue on with the lecture. So if you wanted to draw this circle, okay, you see this right here? This is our magnitude of that h omega, right? H omega, which was used by freaks, or whatever you want to call it. So now I'm going to draw that onto this, okay? Boom, and I just did this for fun. You don't have to. You can if you want. If this helps your brain, boom, go ahead. Someone's like, where's the other half of the circle? I'll show you another half. 2. Boom. Easy, right? Not that hard, right? Everything making sense? Okay. And then let's see. I wanted to show you some roots. And then I already have things already done. My poles and my zeros, I'm just calling this. And if you wanted to make this a lot fancier, because we're engineers and we like making things pretty. Display. My zeros are at, what did I say? %D and %D. And then we use my zeros 1. And how many zeros did I have? I have 2 zeros, and then my zeros 2. All right. Z is equal to that, and Z is equal to that. Does that run? Oh, it don't run. I think it's F print F. Yay, it worked. And then, oh yeah, you gotta do this. That don't work. Back end. Yay, it works. Anyways, and then F. I don't like that. 4. 2.1. There we go. Boom. Easy. Okay, give me another precision. 3. There we go. 0 and 0.636. Okay, that's my zeros. Okay, and then you can do the same. Copy and paste. My poles. Poles are at. How many poles did I have, y'all? Let's see. My poles. 2 poles. Let's see if it works. My poles. Let's see. Let's see if it makes me write a string. I don't know if this is gonna work. I guess someone's gonna have to figure that out. Let's see. Right below in terms of real and imaginary components. And then angry face. There you go. Cool. Anyways, now let's kick some boxes, or not boxes. Let's just do another one. Figure. I don't know. I'm just choosing random figures. Let's do a Z-plane. Oh yeah, look at that. It's our pole. It's our 0, and then that's our thing right there too. And then someone said, "Hey, what does a 0 do?" Okay, if you don't believe me, let's do the following. Let's see if anyone bothers by this. 0.9. There we go. Whoa! What happened here? Let me just do 0.191. There we go. Shouldn't be too bad. There we go. So what happened to our magnitude response? Oh, look at that. What does that look like? High pass filter, zoom, and then does some cool stuff. So zeros are also pretty funny and dangerous. Be careful. If they're too close to your magnitude, unless you want a high pass filter, band stop, band pass, whatever you want. If you wanted to design a band pass, you'd have to put a 0 here, here, and then some other zeros here, and then make sure there's ringing over here. So bring these poles over here or wherever. So then you get this band pass, okay? Band pass, which can look like 1 pi, okay? See, band pass, okay? We're passing just that frequency, all right? That's how you build them. Anyways, 2 pi. And then let's get rid of that. Anyways, back to your assignment. And then boom, boom, boom. And then let's see, residues. So there was an error in your assignment. I already fixed it. But let me show you so you guys don't have to think about it. Boom, residues. So residues is really nice because the whole point, and I'll show you right here, is you remember the Laplace transform where you got partial fraction expansion, right? You're gonna do it again. It's gonna come bite you again, where you're gonna have the following: the inverse z transform, so z to the -1 of x of z, right, is gonna give you x of n, okay? Where you can write any general signals in terms of like residue, and then you got some pole or residue, and then times the pole to the n u of n, okay, and plus I don't know. I think there was some summation of n I is equal to 1, whatever the first one of r of I p of I, and then n u of n, and then there's plus k's, but don't worry about that. They eventually what do you call it? These become delta functions that help just with the gain at the beginning, but honestly don't stress about it. So this is right here. This is your money, okay? Memorize that, okay? So it could be said that what's his name? If you just did like r1 p1 to the n plus r2 p2 to the n, this is your exam, not exam 6. Okay, someone's gonna forget it. They're gonna be like, what the heck? Oh yeah, don't forget this, u of n. Okay, now you get the full point. anyways. So let's see. I end it with this. Residues, let's run that. F9. Oh yeah, I can do F9. Great. So then you get 2 residues, right? This residue goes to this pole, okay? And then this residue goes to that pole, okay? And we're just looking at these poles. The poles are what truly matter. So anyways, you can do the following. This is the cheat way. You can do this. Or it's not cheat way. It's just the way Dr. Stuber tried representing it. But I think an update. So I took our R. Actually, no. Someone's annoyed. Someone's like, Dave, I wanted to pass this exam. R1 times P1 to the nth power plus R2 times P2 to the nth power, okay? And then we only have 2 poles, so just run it. Let's see. Oh, dot. Don't forget the dots. There we go. And that's our step response. Looking good, right? Where does it, what do you call it, settle to? Well, it goes to 0 because it's an impulse. Sorry, impulse response. So don't forget it. Title. Impulse. Yeah, whatever. Oh, well. See, nice. And then, oh yeah, don't forget your time. X label. See, this is where you start becoming picky. Once you understand what things are, then you start getting picky with little things like that anyways. Let's kick our box, okay? So if you wanted to kick your box with a unit step, and this is going to be on the exam as well. Let's see, 6. Let's get you this guy right here. 7. There you go. You guys need to know this, okay? 7 unit step, okay? X is equal to x of n is equal to the unit step. So how do we do this? X of z is equal to boom, infinity to minus infinity of u of n, z of minus n. What do we do? Infinity 0, z to the minus n. What does that look like? It's our geometric series. I copied myself. 1 minus z to the 1 minus z is equal to z minus 1. Is that good? And then we want to run this in MATLAB, okay? So x of n, right? What do you call it? It is said that y of z is equal to h of z times x of z, okay? So if we know our h, right? Our h, we know the polynomials, okay? We've been doing this. And we have our x. So what is this? This is going to be 1, right? And this is going to be 0, correct? This bottom here is going to be 1 minus 1, okay? So, and then our h of z, well, did we do that? Let's see, did I do my h of z somewhere? I think I did. Well, that was number 1. Okay, let me show you. Someone's not believing me. And this is why I tell you guys to derive things, okay? Let's see what angle. Did I tell you how to calculate the gain? Let's see. Where are the poles and zeros? Use the Euler's equation. What else is there? I thought I told you guys to find the gain. No, I thought I told you guys to find the gain. Nah, it's okay. So there's another thing that I want to show you that. What is the DC? What is this gonna settle to? That's what I wanted to say. Let me see. Step response. Residues function. But yeah, anyways, for this one, you need to determine h of z, right? And what was h of z? This guy right here, right? So we need to convolve this with this. And what does convolving mean? polynomial convolution, right? So this is our convolution. We're just convolving this with our unit step, all right? So here's our unit step. My unit step. I don't know, u of b is equal to 1, 0, right? U of a, okay, this is my, okay, someone doesn't like me using numerator. I gotta be picky. Denominator. 1 minus 1. Are you following along? Was this very useful? Anyways, and then I want y num, okay, is equal to the b, right? Wait, conv b, right from our top guy right here. We could have called it something different. This is our impulse. If you really wanted to, you can just call it h or something like that. Anyways, we call it b. Convolve this with our numerator, right? And then y denominator is equal to conv a u denominator. And then what did I do after that? Let's see. Oh, then you could, well, let's just run it. Let's, boom. And then luckily for us, we got a 4x1 or 1x4 and 1x4, so we don't have to use the equal length function. This guy right here again, we don't have to. We're pretty much good to go. But all we need to do is, because we have that, we're looking for the residues, okay? I need to know the residues. So if I do yr residue, y's poles, and y's gains, okay? Residues of y num, y dem. And look at that, we get 3 things, okay? And then if you wanted to do your pole 0 gains, better yet, if you really, if you're like, Dave, I just want to see things. H, would I calculate it again? You could do this dumb thing again, but see. Nah, don't do it. You'll be sad. Yeah, you could do a Bodhi plot of that, or what do you call it? Step response again. Anyways, now we can go back to our thing if you wanted to use this puppy right here. Yeah, that guy. Because we have no K's, don't worry, we're good. We just copy paste this puppy, our actual Y response. Boom. And then we have our same n figure. Now let's just copy paste the figure. Oh, I didn't even do anything. I just whatever. Hey, look at that. Something's wrong. 121. Conv numerator denominator. That's my num. That's my num. Dem. Oh, R, Y, R, Y. There you go. Boom. Yeah, and then what value does that step, or what do you call it, result to? So here's the other part you guys need to know, and this is going to also be on your exam, is the, what do you call it, final value theorem. Let's see. 8. So let's just say you wanted to know what the final value of, let's just do it, 1, what do you call it, 1 over 1 minus c to the 1. So the final value theorem states that you can find the final value, I don't know, some a, or I don't know, we've used too many numbers. You could just do, was it, I think it was 1 minus z to the minus 1 of x of z. Okay, so you got to multiply this, and then you got to evaluate this for z is equal to is it 1? I think that's what it is. Yes, 1. So if you think about it, what's the final value theorem of this guy? So this was x of z. What's the final value of the unit step? So if I did this, 1 minus z to the minus 1 of x of z, which is basically that, you get 1 final value theorem. And that makes sense, right? The final value of a unit step is 1, okay? So if you wanted to do your assignment, which was 1 minus r cosine omega naught divided by 1 minus 2r cosine omega naught plus r squared is z to the minus 2, z to the minus 1, and then this right here is z to the minus 1. All you got to do, what's the final value of this? Well, you already know the final value of this. It's going to be, well, let me see. First, you got to convolve this with 1 minus z to the minus 1, okay? This is our h, okay? This right here is our x, okay? Okay, is that making sense? And then we're gonna multiply this by, what do you call it? So we're gonna multiply this by 1 minus z to the minus 1, okay? Minus 1, okay? So if you think about it, if you convolve the unit step with the impulse response, you're finding out, like, you're turning on the switch. If you think about it, this is an easy cheat step. This, boom, and then you're just analyzing this. So all you got to do is 1 minus r, replace all the z to the minus 1s with 1. Cosine omega naught, 1 minus 2r cosine omega naught plus r squared. And just plug and chug and you'll get your final value theorem. And if you don't believe me, just crunch those numbers and you're gonna get this puppy right there, 0.68. You wish it was 0.67, right? There it is. 666. Yeah, there you go. Anyways, is that making sense with everybody? So, and then let me show you the other parts. State space. Okay, and this is where I need you guys to put more work into this, or not more work, it's just to prove your work, where you're gonna redraw that system as a term of this, what do you call it, a direct form 2 block. So we're going, the fingers for a transform go up, so we're going down the waterfall. So 1d, we got another d, and then we want our feedback path to be right here. Here's A0 minus, A1 minus, and then here's our B1. You see how I can draw these, and then plus x of n, and then was there a B0 term? No, it's just a wire. Boom. There you go. Let me remember. I don't remember my gain. Yeah, I had a 1. Okay, there's a 1 right there. So B0 is equal to 1. It's just a wire, okay? Plus. Okay. Oh! I wasn't even showing you guys what I was doing. Anyways, you see, this happens when I start streaming, so let's reiterate what I just did. Going down the waterfall, D, and then I did my feedback, okay? Feed forward, okay? That's how we do direct form 2. I set Q1, right? Here's our n plus 1, here's our Q, and it gets delayed, turns into Q1 of n. Here's a Q2 n plus 1. That gets delayed. Current state, current inputs are going to define our next state. Current state, current input define our output. You can solve this equation, boom, and then get your Q's, you're done. Oh, Q of n plus 1 is equal to whatever this guy is, and this guy is, so minus a0 q1 of n minus a1 q2 of n. And then I'll let you guys do the mathematics on that one. So engineer, if you wanted to get the answer, this right here will calculate that. So 9 is to just say, hey, can I do it? And then 10 is to say, yes, you can, or oh, just check your work. And then, yeah, do your SS equations. Don't forget that TF function, 0 pole DC gains, PZ map, impulse. You're doing the same assistant. And then in your own words, how can you use this assignment to model any system in the future that you see? So maybe you want to create a function that like just does your 480 homework or whatever, because you're going to be doing more sampling. You're going to understand what the Z transform truly does. And then what happens when you sample a sample and then you start going into this DFTs or discrete time Fourier transform. So it gets a little messy, but anyways, that's pretty much it. So, and then I guess the last thing, if I were to really just save you guys, or I don't know, I don't even know if I'm saving anyone, or maybe I am, I just don't realize it. Is this useful? I don't know. Sometimes I think it's not. People are like, yeah, we need more. Okay, I'll give you more. Don't forget the thing where you have I think it's called the unilateral Z transform, where if you had a condition, what was it? Y of n minus 2, right? You're going to have the following, where it gives you yz of, what do you call it? Well, yz z minus 2, right? And minus, what do you call it? No, shoes. Wait, okay. Y of n minus 1 is going to give you, if I were to do the Z transform, that y of z to the minus 1 minus y of 0, that initial condition. I think that's what it was. It's like the difference equations. Let me see if I can show you. Z transform differentiation property. Let's see if I can show you this. It's this puppy. Where is it? Where is that little guy? Differentiation? No, this and all these equations dumb. Where's our derivative? No, we're not trying to take a derivative. We're just doing the Z shifts, and we'll show you later. Hopefully, Dr. Stever will show you something. Let me see. Is anyone doing that or reading the actual homework, or not homework, the actual notes? Let's see the Z transform. There you go. ComSys. Parent directory. Where are the notes? The notes are right. Parent directory. Come on. Notes. Z transform. There you go. So yeah, memorize this. Yeah, memorize the whole thing, Dave. I know. Let's see. One last thing. Cross this off because he was like, no. And he had a fit of rage and said, no one's gonna listen. Anyways. And then, oh yeah, here's this partial fraction expansion. Memorize this. Boom, residues, poles. Okay, easy. Then boom, you get your thing. Okay, don't forget that. Oh yeah. Oh yeah. Make sure it's stable. Power series, ew. Don't do power series, you'll be sad. And then oh Alright, if you stayed to the end of this video, suppose you were like, Dave, how did we what is, how do I, like, you know, oh, look at that, cosine omega not n. You see where you're getting this. What does he do? He just turns them into two separate e to the j omega n's, okay? And then he said, well, if you think about it, here's the pole, boom, boom, and then just multiply, boom, you're done. Yeah, he's really getting y'all, okay? He's really getting your money's worth. And then shifting in time, don't forget that, multiplication. Where's the money making questions? These questions are making me sleep. Convolution. Derivatives. Ew. Don't do derivatives. You'll be sad. Where is the money making equations? He starts talking about the unilateral. This is his whole textbook. Everyone, just print this out. He might delete this and then make it his own textbook. Systems. Boom. What else is here? Oh, shifting in the time domain. Is this it? I think this is it. Yeah, this is it right here. Z to the minus 2, z to the minus 1. Z to the minus 1. Is that our problem? I want to see if it gives you an exam problem. And then, oh yeah, ZSR, ZIR, memorize that too. And then, oh, this is an exam problem. Don't see it. Blank. Anyways, definitely do this problem because I think this actually might be your exam problem. And it gives you all the steps. So anyways, in that case, there's not much for me to talk about other than this assignment shouldn't be too bad. If you think about the actual, what do you call it? Second half of the Z transform, it's literally plug and chug. You just need the, what do you call it, control systems toolbox to run the assignments. So other than that, no, that's pretty much it. So what do you call it, this will be the video for Wednesday's discussion. Go ahead, watch this on your own time, whatever you want. And other than that, I think we have a study week next week. We'll do a final meeting. We'll talk about whatever you guys want to do. And that's pretty much it. All right, y'all. That's another video. All right. Have a good day, y'all.